Welcome to another podcast. In this episode, we're going to be taking a look at a second-order differential equation and construct its solution using the Laplace transform method. I'll try to tie this back into the previous video that introduced the input-free and state-free solutions, as well as tie it back into things we did earlier in the semester. So starting here, we have, I want to look at the equation y double prime minus y equals e to the negative t. And remember, we have to supply initial conditions here. So my initial conditions are going to be y at 0 and y prime at 0 equal to 0. You're not going to be doing any general solutions in this chapter. Everything is going to be IVPs that we're solving. So I start off by taking the Laplace transform of both sides. The Laplace transform of the left side is s squared y of s minus s y at 0 minus y prime at 0. That's for the y double prime term. That's the Laplace transform of y double prime. And then minus the Laplace transform of y is just y of s. This is equal to the Laplace transform of the right-hand side, but for right now I'm just going to call that f of s. We'll come back to that in a second. Alright, if I group terms over here, I get s squared minus 1 y of s. Keep in mind that this is the characteristic equation. And that's equal to f of s, and then if I subtract over s y at 0 is 1. So that would be adding s to the other side. And then here, minus y prime of 0, but y prime of 0 is 0. So this piece is 0, this piece is 1, and so at this point I am done. If I then solve for y of s, that gives me f of s over s squared minus 1 plus s over s squared minus 1. And so I need to look at the inverse transforms of each of those pieces. So let's start with the inverse transform of f of s over s squared minus 1. Well, the Laplace transform of e to the negative t is 1 over s minus a negative 1, which would be s plus 1. So looking at this, this is f of s over s squared minus 1, which is 1 over s plus 1, s squared minus 1, which is 1 over, this is the difference of squares, so you've got an s plus 1, you've got two of those now, and an s minus 1. So in order to do this particular problem, I need to sort of figure out how to do the partial fractions decomposition for this inverse transform. And so if I look at just this, then I'm looking at 1 over s plus 1 squared times s minus 1, and I'm going to break that up into an a over s plus 1 plus a b over s plus 1 squared plus a c over s minus 1, and then I can use cover up to find the values of a, b, and c. So for example, b, using cover up, I would cover up the s plus 1 squared, so I would plug negative 1 into everything that's left, and that would give me negative 1/2 for b. Similarly, if I cover up s equal to 1 for c and plug everything else into what's left, I would end up with a 1/4 for c. And then for a, I would end up with a, let's see here, I just got to plug the values back in and make sure that it equals 1. So if I used 0 for all of the s's to find a, then I would have a minus 1/2. If s is 0, that would be a 1 in the denominator, plus C is 1/4, and if I had a 0 for S in the denominator, that'd be negative 1/4. And that has to equal 0 when I plug in S on the right-hand side. So S equal to 0 on the right-hand side would give me, it looks like negative 1. And so let's see if I can get this going here. So this would be minus 3/4 added to the other side. Looks like negative 1/4. So that's the value of A. What that will do then is I can replace my inverse transform now with negative 1/4 over S plus 1 plus negative 1/2 over S plus 1 squared plus 1/4 over S minus 1 and hopefully I recognize the inverse transforms of each of those. The first one's pretty easy. It's just negative 1/4 times e to the negative t. That's its inverse transform. This one, because it's a S plus 1 squared, we've got a t involved in the problem. So this is minus 1/2 t e to the negative t. And then finally this last one is 1/4 e to the t. And so that would be the state-free solution for this problem. So remember that the state-free solution to this problem is the solution to the problem when the initial conditions are 0. So if I solve this, in other words, this solves y double prime minus y equal e to the negative t. And with y of 0 equal to 0 and y prime of 0 equal to 0. That's what this solution is. If you were to go back and do that the way we know how to do these problems, that's what you would end up with. Similarly, so I've taken care of that here. Now I need to look at the inverse transform of this bottom one. And the bottom one is s over s squared minus 1. So it would be s over s squared minus 1, which I need to also look at the inverse transform then. If I factor the denominator, this would be s plus 1, s minus 1. But I want to remind you of a formula that we looked at in class, and that is the Laplace transform of the hyperbolic cosine of t. Let me do the hyperbolic cosine of omega t, because that's the formula we did in class. The hyperbolic cosine of omega t is equal to s over s squared minus omega squared. And so you can clearly see, comparing this with this, that what we are in fact looking at for this problem is nothing more than the hyperbolic cosine of just t, because omega here is clearly equal to 1 when I compare this with this. So that is our input-free solution. And if you wanted to rewrite that in terms of exponentials, remember that that is 1/2 e to the t plus 1/2 e to the negative t. And what you can do for your final answer, if you would like, is combine them with the pieces above. Now you don't have to do that. I wanted to, in this example, specifically show you the input-free versus state-free parts of the problem. Remember the input-free solution. So give myself a little room here. The input-free solution is solving the differential equation, the homogeneous version with the initial conditions from the IVP that we're looking at here. So that would be the solution to the input-free problem, and we also have the solution to the state-free problem. So let me just let me go ahead and box those up, just so when we're done we have a nice view of this. We had two solutions here. One is the state-free and one is the input-free, and together those are the solution to the differential equation. All right, thank you for watching.